Alrighty, friends. I'm going to start a minute or two early because I've got a ton of slides and I don't want to have to start rushing at the very end. Before I begin, my name's Ankush. I'm a software engineer at Quizlet here in San Francisco. I've been involved with the Quizlet Android app for quite a while. I wrote its first lines of code as an intern a little over 6 years ago. I'm going to start by sharing a teeny tiny bit about what Quizlet is, what our history is, to kind of set the stage for how and when and why we decided that shared code was something that we wanted to invest in. I'm also going to give a kind of super brief overview of a few different approaches that other folks have taken to shared code so that you can kind of have a more big picture idea of the ecosystem as a whole. And then I'm going to get into the juicy part. I'll start talking about Quizlet's specific journey with shared code and lessons we learned along the way, and why we ended up deciding and how we ended up evaluating Kotlin Multiplatform as our current tool for sharing code. So, for folks who don't know about us already, Quizlet's mission is to help our users practice and master whatever it is that they're trying to learn. We provide tools for our users to create and share knowledge with each other, and we also build experiences to help our users learn the information that other folks may have shared with them or that they may have shared with other folks. Like a bunch of startups, Quizlet began as a product for a single platform, and that platform is the web. Our core product offering was essentially user-generated digital flashcards so that folks could, originally it was designed just to memorize vocabulary.
It's 3 o'clock.
And things were simple back then. In order to assess if a user had mastered some vocabulary, we would pick a random element from this big list of words that they're trying to study, ask them to type in an answer, and if what they typed in matched what the database said the right answer was, they got it right. It was just a basic string equality check. Things were super, super simple back then. And things change over time for the better. As the years progressed, Quizlet spread from learner to learner, from educator to educator, and we started growing. We had tens of millions of users before we knew it. Millions of sets of study material were being studied on Quizlet, spanning thousands of different subjects across several different modalities that users want to be able to interact with their content in. And things, all the different permutations you can imagine here, different types of users, different types of study material, things start getting really complicated when you have that amount of variety. And in order to handle this, we basically needed to be smarter. We started doing some stuff to basically create specialized domain-specific logic to make this process as easy for our users as we could. Some examples of things that we built were things like standardized analytics events so that we can track learning outcomes. Because if you can't track if your users are learning things more effectively, you can't evaluate if your new features are helping them learn things more effectively. We built things like context-dependent grading rules where, if a user's studying math, or if a user's studying German, or if a user's studying chemistry, things like basic string equality aren't really the best way to evaluate if a user knows the answer or not. And we've gone all the way down to using the latest kind of brain and cognitive science research out there to model how a user's answer history might predict what the most useful thing for them to be studying is, so that they can better learn and retain information over time. And each of these things is super important and super closely linked to Quizlet's mission of making education better and more accessible. And each of these things also requires a pretty deep domain-specific understanding of Quizlet's specific product and Quizlet's specific market. It's a lot more advanced than what it would take to just build a simple application that reads and writes to and from a database like we originally had. So we basically went from a web client that talks to and from an API, something pretty simple, to something a lot more complicated, where we had this, what started off as just a simple front end to talk to the web became pretty feature-packed. And all of these things that are in there are very important, but it's also very complicated. And this is what I like to call our secret sauce. The secret sauce is kind of what takes an app and kind of elevates it from a view into a database. into a product that can deliver delightful experiences to our users. It's directly responsible for empowering users and helping them learn things at Quizlet, and it's also a big reason why we're able to build a product that is pretty solid and can outcompete many other competitors out there. And it's easy to see that continuing to invest in the secret sauce lets you build a much better product. But Quizlet was starting to reach a phase where it was easier said than done, and that's because we needed to build our mobile apps. So rewriting the secret sauce across multiple platforms is tricky enough if all your platforms are starting from the same place and you're writing it once on all 3 platforms. But the reality is our mobile teams were building out standard API interactions, standard UIs. We didn't have the resources to build those and at the same time re-implement the secret sauce that was already kind of established on the web. So if we wanted to continue to make Quizlet more magical for our users and build cool new things, we had to kind of address this problem head on. And one option that we had was, hey, let's declare feature parity bankruptcy. Maybe we just wouldn't support these features on mobile clients. We would make the mobile clients just talk to the API, and that's it. Like if you wanted to do some of the more advanced stuff, you had to use the website. The more literal interpretation is that we probably would have to stop doing this as a client-side feature. We would do something like gating all the secret sauce behind the API, and that's the only way for the mobile clients to use the sauce is just by talking to the API. And for many businesses, this might make a ton of sense. If you're a bank, you probably don't want all of this stuff being on the client anyway. But at Quizlet, we have a ton of younger users. We have learners in developing countries who are using mobile devices as their primary way of using apps or consuming services online. And they tend to have less reliable connections to the internet. Furthermore, I think our secret sauce was in an interesting place. If it was something like a content recommendation where you only have to call the server a few times per session. This is something, maybe it's something that could be run in the background, something that you could cache the result over time and show something stale if you needed to, and maybe even fall back gracefully and say, hey, sorry, like you can't, it's like we don't have any content to recommend to you right now. That might be completely fine in many apps as well. But for Quizlet, things like grading a user's content that they answered and suggesting the next thing for them to study as they're studying through their study material is something that we didn't want to introduce friction to. If it took even like a single second, it would pretty drastically harm the studying experience for our users. And so for that reason, we basically couldn't do this kind of an approach where the client just talks to the server 100% of the time. So the other option was, hey, let's take a breather. Let's stop writing more secret sauce so that the mobile teams can finish catching up to where web is and re-implement it 3 times. And that might work, and there's ways that folks have explored where maybe you invest in a common test suite to test that logic is consistent across platforms. But still, if the secret sauce is what got us to have such a successful web app, we understandably didn't want to just slow down so that we could catch up on mobile. And that's what kind of led us to this inevitable conclusion that we had to invest in our secret sauce. And for some businesses, this might just mean let's just hire a bunch of developers so that we can rewrite it 3 times and keep going from there. We did not have the money at the time to do that. So the approach that caught our eye was investing in our ability to write our super specific, domain-specific code once and share it across platforms. So let's take a look at a few different popular ways in the industry right now that folks do this. One approach is kind of this share all the things approach. And the promise is you hypothetically can write your app once and run it on multiple platforms. And when I say app, I don't necessarily mean your entire app. In Quizlet's context and in the context of many companies out there, it's more like probably like a feature slice. Like you pick a feature and you try to implement that entire feature using whatever code sharing platform that you want. And some examples of this are React Native at Airbnb, Pinterest, and Nextdoor. A more popular example nowadays is something like Flutter. And unfortunately, many of the large companies that were pioneering in React Native ended up having to discontinue their use of it for a variety of factors. Some of the realities were that there's a huge reliance on bridging infrastructure, and a lot of the companies that were trying to use React Native ended up having to spend a lot of time writing and maintaining this bridging infrastructure themselves. it's difficult to seamlessly integrate with existing native apps, which is where Quizlet was kind of coming from, and which is where a lot of these bigger companies were coming from as well, where if you have a team that is split between writing native code and writing React Native code, it can be a little tricky to manage just the organizational aspects of it before you even start to deal with the technical aspects of how you cross that boundary. Performance issues are pretty commonly, commonly cited reason why React Native isn't great, mainly due to differences in the threading models. UI can end up feeling non-native because you're using abstractions across platforms. And things like the less mature frameworks and libraries mean that it's a little trickier to deeply integrate with the OS that you're working on. And again, that means that you might end up spending time on the bridging infrastructure instead of writing the code that you're trying to write. Here's a quote from an engineer at Nextdoor. Basically, the quote is, "Every company that I know of that has tried this hybrid approach has walked it back months later. The companies that seem successful with React Native seem to be the ones that have their entire app in React Native and started out the app that way. We're still in the process of winding down React Native here at Nextdoor." And so this kind of does a pretty good job of consolidating the things that I'm trying to say. It's not that React Native is bad. It's that when you end up trying to build a hybrid app, you end up also having to deal with the downfalls of the kind of approach where you have to bridge this gap at some point or another. So another pattern out there is sharing non-UI code. You know, if sharing UI code is pretty bad, how about we just don't share UI code? The idea is, you can write native UI, and then you can write non-UI code only once. And again, maybe you'd write a native UI for a specific feature, and then the non-UI code for that feature only once. And some examples of this are were C++ at Dropbox, Slack, and safety culture. And so Dropbox, there was actually a talk earlier today about a blog post about how they had used shared C++ to power features like syncing camera rolls, and that ended up introducing a downstream dependency on things like file I/O, networking, storage, and they ended up not having a great time with that. And so some of the realities here, niche tooling with things like Dropbox, where they had to maintain their own library to generate JNI bindings. It can lead to hiring and retention issues. Like if it's not fun to work on your code, people will work where it's more fun. It requires things like strong concurrency support if you end up having to rely on storage and networking and concurrency. And there's potential performance and typing issues specifically at the boundaries. I think C++ is relatively performant when you're within C++. It's pretty darn performant. But then when you end up at the edge where you need to talk to Java, that's an interesting place where performance complications can arise. It's also much more difficult to share code with front-end web, like was a requirement for us. And some things just need to be different across platforms. It can be a little tricky when you're writing shared C++ code to say, like, hey, if I'm on iOS, talk to this part of the iOS system, whereas if I'm on Android, do this differently. And a quote from the Dropbox blog post was, "Although writing shared code once sounds like a great bargain, the associated overhead outweighed the benefits, which turned out to be smaller than expected anyway. In the end, we no longer share mobile code via C++ and instead write code in platform native languages." Slack also recently had a blog post announcing that they had stopped developing their internal C++ library a while ago, and they instead rewrite their implementation across clients and had invested in some engineering organizational changes to make sure that those things were consistent. The quote here is, while we are no longer building a shared library, Slack still needs to maintain consistency and reduce duplication of effort while developing separate implementations of client infrastructure." So now what? Common threads with some of the previous things were their reliance on cross-platform abstractions for UI, for persistence, for networking, for serialization, for concurrency. And relying on cross-platform abstractions for that kind of stuff, from what we've seen, tends to either oversimplify to the point where you have to bypass the framework to do what you're trying to do, or overcomplicates to the point where it's no longer fun to actually write the code because you have to maintain all sorts of weird edge case logic. So where does that leave us? While it would certainly have been nice to write our entire code base once and share it everywhere, all of the engineers at Quizlet, and hopefully all the engineers in this room, kind of know what resources they have at their disposal to build UIs on Android and across other platforms to build and interact with APIs, to interact with local databases. What's a lot more complicated at Quizlet were the things like the ins and outs of German language grammar. Keeping up with cognitive science research so that we can help our users answer the right questions instead of wasting time on things that they might already know. So what we decided to do was share our secret sauce instead of building shared abstractions around the database or around UI. Unlike a bunch of other companies, we basically had this product requirement that our secret sauce had to be on device. So we had a little bit more pressing concerns and iterating super quickly on shared UI across platforms. Our secret sauce also doesn't rely on things like the fine-grained details of like network conditions or disk I/O like Dropbox ran into. And that made it a particularly great candidate for shared code. So how exactly did we do it at Quizlet? We used JavaScript. Our first attempt at sharing code was to reuse what we had already written for the web. The Quizlet secret sauce was originally written in JavaScript to target our web client, so why don't we just spit out a JavaScript artifact and shove it into our mobile apps through a JavaScript engine? And we were able to do that. We were able to spit out standalone JavaScript artifacts for each aspect of our secret sauce that could be consumed in the mobile apps. We would bundle that file into the app and run it through an on-device JS engine. We would use disk I/O to read this big file into memory. We would take that string and pass it into whatever flavor JavaScript engine we were using at the time on the mobile clients, and we would be able to interact with it to some degree or another, with pretty sizable performance hits, but it worked. It was far from perfect. Unlike real native code, interacting with strings and weird non-standard objects is not a fun way to write code. It was pretty error-prone, where we didn't have any compile time safety of what exactly are we passing in. We would be constructing long strings to call into functions that hypothetically we knew were supposed to exist in this minified JavaScript file, but it still worked. None of this shared code was being run in a first-class mobile runtime, and so debugging stuff when things went wrong was not very fun. Figuring out why crashes were happening was not very fun, but it worked. On Android, we had to use a library called J2V8 because it was the only one that was performant enough to run this giant complicated rule engine or to use these giant complicated state machines. And that runtime uses JNI to talk to an instance of the V8 JavaScript engine compiled down to C++. It caused our APK size to almost double, but it still worked. And this isn't even mentioning the general disdain for JavaScript among all of our mobile engineers at the time. So front-end web developers may have felt comfortable writing this secret sauce in JavaScript, but mobile developers didn't really feel comfortable consuming it, let alone trying to write any of it, but it worked. And that was a huge win for Quizlet. Just getting to the point where we were able to unblock our mobile clients from being able to write and use these features that are pretty central and core to the Quizlet product was a huge, huge, huge win. We were able to do this because we focused on state machines and rule engines. We were able to do this without committing our apps to being in some complicated framework, because this was just a black box that we could pass things into and get the new state out of. We could use whatever architecture we wanted to in our apps. The iOS app didn't have to use the same architecture as the Android app, which didn't have to use the same architecture as the web app. And we learned a bunch of key lessons from this experience. The first is clean interfaces are great. Writing code with clean interface boundaries made it super, super awesome when we had to extract them out later to be used as shared code. If we had intermingled our web UI code with this secret sauce code, it would have been a nightmare to get that same code to run again on Android or iOS devices. So by isolating our vital business logic into those state machines and pulling them away from the regular application code, we were able to build and use clean interfaces in our shared code. We also learned that it's very important to aggressively validate inputs and outputs from shared code. It's really easy for misunderstandings about the meanings of parameters to arise when you're building complicated modules that are being consumed by developers who might not have had any input in actually writing the module itself. And aggressively validating for unexpected input, especially in a loosely typed language like JavaScript helps minimize those issues that might arise due to miscommunication or due to under-documentation. I hopefully don't have to explain to everyone in this room why tests are good, but tests are extra good when you're writing shared code. With shared code, it can be a pain to debug in a host client, like I mentioned earlier, where if you have a JavaScript file that you're trying to run, you don't want to have to debug that code. So properly tested shared code is code that you don't have to spend as much time debugging on a host client. Properly tested shared code is code that you also don't have to go back and make changes to. It takes a little bit of effort to, find a change that you need to make due to a bug, go back into, let's say, JavaScript to make that change, repackage all of that into a nice little artifact, and reship it again into the mobile app just to test if it worked. If you have tests that do that for you and that catch those kinds of issues earlier, you save a lot of cycles compared to, the same approach might work just fine when you're writing regular native code where you just test by manually seeing if it worked, but that doesn't really fly when you're writing shared code. It also gives you confidence into code that maybe we own as a company, but as an Android engineer, maybe I wouldn't feel confident messing around with JavaScript, but just knowing that it's tested thoroughly means that I can feel more confident in using that code that technically we own as a company, but I don't know how to debug myself. And as I mentioned earlier, state machines and rule engines are super good candidates for sharing. This allows you to decouple kind of how your app's logic works from how your app architecture works, and you can share the complicated business logic of your company across your apps without necessarily needing to make sure you're using MVVM everywhere, or without using whatever architecture you want to use on one platform doesn't leak into every other platform that you're using as a result of sharing the code. So I've spent around 20 minutes talking about things completely unrelated to Kotlin Multiplatform, and the title of the talk has Kotlin Multiplatform in it, so it's probably time for me to start talking about it. Hopefully, most of you are familiar with Kotlin in general. In 2017, Google announced that it was backing Kotlin through the Kotlin Foundation, and it became officially supported on Android, which is really great. And at KotlinCon that year, JetBrains announced the concept of a Kotlin multi-platform project. The idea was to take the model of Kotlin's JVM interop that made it so successful within the Android world and within the world of folks who are writing back-end servers, and to basically replicate that in other environments. In Kotlin multi-platform, you generally have this set of code called your common source set. You write code that's completely agnostic of platforms. You can't use things like java.util.date in your common code because your common code doesn't know about Java at all. You can use standard Kotlin concepts, like you can make a list, you can use ints, you can use longs, but the interop layer is nowhere touching your Kotlin common code. Then, through Gradle, you can configure multiple different compilation targets for that common code where you might be able to specify a little bit more platform-specific logic that you need to apply. There is Kotlin JVM, which lets you spit out jars. It lets you spit out AARs for Android. It lets you spit out entire Android applications if you want to. There's Kotlin JS, which lets you spit out artifacts for not just in the web browser, but also for, let's say, Node.js environments, which are considered two different targets for the sake of Kotlin JS. And there's Kotlin Native, which lets you spit out basically anything under the sun. You could spit out iOS frameworks. You could spit out binaries for Mac, Linux, and Windows. You could spit out code for the Android NDK. You can write like a watchOS app for iOS if you really wanted to. You can spit out anything you want with Kotlin Native. But the important thing here is that they're each considered separate compilation targets. You can't use code for the JVM in your Kotlin JS artifact. But the idea here was that you can write your code in Kotlin and actually spit out first-class supported framework types, artifacts for each platform, which sounded much better than the approach that we were using for shared code, where you had to run it in an external runtime like with JavaScript or with something like JNI, like you can currently do today with things like Go and Rust and Dropbox's Genie library for C++. And so yeah, the idea that we could have real JavaScript artifacts, real jars or AARs for Android, real Objective-C frameworks for iOS is super enticing. And being able to get all of that with the backing of JetBrains and Google, which have proven track records in a lot of this stuff, with all the type safety guarantees of Kotlin in a language that was fun to write in, seemed like a no-brainer to at least explore and validate. And so this is more or less how we envisioned our Kotlin multi-platform kind of framework fitting into our shared code setup, fitting into how we think about our clients today. It kind of puts Android and iOS on equal footing with our web client, which was something that wasn't really the case before when the shared code was part of the web client. And basically, we would write our secret sauce in Kotlin Common, apply the target platform, and maybe do some platform-specific things that need to happen to spit out a platform artifact, which we just consume on our client. We'd spit out a different platform artifact for each platform, and each client would consume it as if it were a real library for that platform. And then you'd use standard interop so that you could, the same interop that we use for JVM in Kotlin, you'd use Kotlin's JS interop or Kotlin's Swift or Objective-C interop to consume in your client. But what does that actually look like? What does that interop look like for non-JVM languages? So as I mentioned, in common code, you have no concept of what your platform is. You're completely platform agnostic. And so when it comes time for you to do something where you actually need to know what your platform is, you can declare your functions or your classes. You can mark like a function or class name as expected. So you see that special expect keyword right before the function platform name. And in the next method, getGreeting, we can just use platform name as if it existed. And you can continue to declare whatever you want as expected in your common code, and the rest of your common code will compile as normal, assuming that that already existed. Then when you're actually targeting a platform, the Kotlin compiler will yell at you when you try to build without declaring an actual implementation for every single thing that was expected in your common code. So you can do things like just say, hey, this platform name is a string Android if you wanted to. But what's a little more fun is that depending on your platform, you actually get to use the same platform APIs that exist on that platform. So on iOS, while you can't use java.util.date, you could use the entire UI device API to get things like, am I an iPad, am I an iPhone, am I an Apple Watch? You can get the current system version. You can do anything that you want using actual Objective-C frameworks that are built into iOS. And the same applies with the web, where Kotlin.js lets you get access to all of the web-specific APIs. So while the downside is that you can't use things like your Java classes that you might be used to in your common code, the benefit is that you get to use all of those things on all the other platforms when you need to use them through this expect and actual mechanism. So what was really the right way for us to test out Kotlin Multiplatform at Quizlet? And how would we actually evaluate if this was a successful tool for us? And so the way we decided to evaluate Kotlin Multiplatform was kind of along those same strength and weakness faults that we saw with JavaScript. Things like, it needed to work because debugging is never really fun when you're working with shared code. It needed to be performant, which was a big issue on Android and iOS. It needed to be stable. And it needed to be something that developers felt confident working in. So first, we had to write something to evaluate. We had to choose an arbitrary part of our secret sauce to port and evaluate, and we decided to start with our grading logic. There's a bunch of complicated regular expressions in there, but it's a decision tree beneath the hood. It's a lot of control flow logic. And it had a pretty concise interface, which was, I think, another also an important part for us to kind of choose a narrowly scoped part of our secret sauce. Luckily, it was relatively straightforward to take our already cleanly isolated JavaScript code base and re-implement it in Kotlin. And in fact, there was just a lot of copying and pasting and clever find and replace to make sure that our code was valid Kotlin once we copied and pasted it over. And we were actually pretty quickly able to get Kotlin to spit out a JavaScript file and a jar that were hypothetically both supposed to be our grading library. But as most of you know, compilation, just because you get something doesn't mean it works. And the fact that we had a so-called Kotlin JS grader doesn't really mean much if it's not working properly. And thanks to our test suite that we'd already written for our shared code earlier, we were able to basically take this JavaScript grader, which had the same interface as our handwritten JavaScript grader, and run the same integration tests for our old shared code with this new Kotlin JS artifact. And we run the end-to-end tests and it works. Do you trust that it's all perfect? No, you still keep going. So we decided to port our unit tests that were testing the internals of this grading logic over to Kotlin as well. JetBrains provides this library called Kotlin Test. It's officially supported by JetBrains, and it consists of a bunch of annotations and utilities to write multi-platform unit tests. It's a JUnit style API. It's pretty standard. It doesn't give you a lot of the fancy stuff, like behavioral tests, but it lets you write real unit tests that let you test things out. And one of the most important things is that it supports a bunch of different test runners. So it's JUnit style test assertions, but they're multi-platform tests. So you can run it in a wide variety of different test runners across a wide variety of platforms. So using Kotlin Test, we were able to rewrite our old suite of not just integration tests, but also actual unit tests for each individual component of our grader to also make sure that that grader was correct. But we didn't really stop there. We were super happy we had end-to-end tests working, we had unit tests working, but we weren't just going to ship this into production because it's a super, super, super core part of the Quizlet, Quizlet experience. You didn't want people being marked incorrect when they should have been being marked correct. Maybe there were gaps in our testing API, in our test coverage, because there's a wide variety of languages. Maybe we had a mistake in something in particular. So it's really scary to think that some underlying hijinks that might have been accounted for with Kotlin Test, that might have been accounted for internally, would hypothetically cause issues when run on a different web browser, for example. And so for this reason, we kind of went all in on validating correctness with our new grader. We basically ran this grader against tens of millions of real-world user submissions. We ran our handwritten JS, our old shared code. We ran the Kotlin JS artifact, and we ran the jar, the Kotlin JVM version, all against tens of millions of real-world user submissions that captured basically the wide variety of permutations and combinations of things that people could be studying on Quizlet. And we had zero discrepancies. It was kind of scary to just have zero things that are different, because you generally expect something to be broken, and then when you fix it, it's fixed. But it really worked. And things that we learned along the way with just integrating Kotlin JS with our existing build process. Going from part of the web code base to an external dependency was a little tricky for some of our web developers to get used to. As mobile developers who were consuming these JavaScript artifacts, we were already used to this. This was just our reality, that we had to pull this thing in and trust that it worked. But a lot of web developers were familiar with, let's change a line, wait for our hot reload environment to just have it updated and see if it works. And that was something that web developers needed to get used to, that you had to build this, test it outside of the web browser, and then assume that it works, or you have to go back and fix it again. So clearly defining contracts in advance and testing it thoroughly just became a little bit more important, because it applied to everyone and not just folks who were consuming this artifact blindly. We had to build a bunch of custom Gradle tasks to create and deploy NPM packages so that we could consume them from the web. And particularly annoying for us was that Kotlin JS is currently still spitting out ES5 compatible JavaScript code, which it works in the web browser, but there's a lot of web tooling that you unlock when you're using newer versions of JavaScript, including tools like Webpack's tree shaking, which is basically the equivalent of, I would say, ProGuard or R8 in Android, where they shake the trees and whatever's not connected to anything that falls out, you just delete from your app. Luckily, Kotlin JS provides this tool called DCE, or Dead Code Eliminator. And it's a Gradle task that you run to strip out things from your code. And it was a modest web bundle size increase of 30 kilobytes, which it's not nothing, but it was very acceptable for the web team. And one of the other annoying things for the web folks is that there is currently no automatic generation of something like TypeScript type definitions. So that's, along the public API, we have to look at what these methods are and declare, like, this is the type that you're allowed to pass in order for our web client to have type safety when interacting with it. Performance numbers. Compared to pure.js, our Kotlin.js code runs around 3 times slower in browser. But all of these units are milliseconds. It's still very fast. This was also a straight port. We didn't do any sort of work to optimize Kotlin.js performance beyond just, let's just use dead code eliminator to get rid of stuff that doesn't belong in here. There's still, plenty of room for improvement here with how we do things. But just, having, in the worst case, a 1.5 millisecond increase is completely acceptable for us in our use cases. On Android, were there any quirks? No. It's Kotlin. You just build a jar and pull it in. It was infinitely better than manually updating a JavaScript file in your build. It was infinitely better than, hoping that the method definitions didn't change from underneath you and you don't realize until you go into production. Compile time errors, those weren't really a thing anymore because if it was an error, it was important because the method signature changed. And on Android, performance was a lot faster. We used the same benchmark that we used to choose J2V8 in the first place when we compared it against a bunch of other JavaScript runtimes. And we compared it against just regular Kotlin JVM code that did the exact same thing. And it did it a lot faster, as you could imagine. There's no beefy runtime to initialize, which saves us a second and a half. There's no need to serialize and deserialize data and marshalling time between our plain old Java objects or Kotlin objects and what J2V8 needed. That's not an issue. The grading logic is also a lot faster. It's just all around a win on Android. And we were able to get rid of J2V8, which is a huge deal. We were able to get our APK size almost halved as a result of switching to Kotlin Multiplatform. I talked a lot about how Kotlin.js compares to our handwritten JavaScript code. I haven't really talked at all about Kotlin native at Quizlet and how multi-platform kind of fits in with that strategy for us just yet. And at the time that Quizlet was originally investigating multi-platform, native was very, very, very much in flux. The Kotlin native Gradle plugin was completely separate from the Kotlin multi-platform Gradle plugin when we were first starting out. And we basically just skipped it the first time around. We were intentionally building a JavaScript artifact with Kotlin.js that was binary compatible with our old JS artifact. We figured, let's try it out for the web where we anticipate the most pushback, and let's just drop that JavaScript artifact into the iOS app and see if it also works. And it did. The JavaScript performance was very, very, very negligibly different. So yeah, that approach worked for us for quite a while. But all that kind of stuff has changed. We are using Kotlin native right now in iOS in production as well. Some of the quirks that we ran into when we were trying to do this was that the biggest one is that Kotlin native builds Objective-C frameworks. It does not build Swift frameworks. So you have all of the limitations of Objective-C and Swift interop when you're trying to use a Kotlin native framework. This, it's not just all the limitations of Objective-C interop. It's if you can represent a concept in Kotlin and you can represent the exact same concept in Swift, but you can't represent it in Objective-C, you lose granularity when you're going into Objective-C, and then you have to maybe manually specify that in Swift when you're consuming it, which, it's still better than JavaScript, but it's not ideal. The other thing is that fat frameworks are not automatic. With iOS code, our developers are used to being able to run, a framework in the simulator on their computer, which is a different CPU architecture than on phones. And until recently, you had to support multiple CPU architectures for phones as well. And so there's this concept of a fat framework where you build the same framework for different architectures and you merge them together. It's not automatic. It used to have to be a very manual process, and JetBrains has at least added a Gradle task that does it for you, but you still have to manually call it. Exceptions are very different in Kotlin than in Swift. Kotlin has no real concept of checked exceptions, and Swift only has checked errors. You can annotate Kotlin functions with this @throws annotation, but if you forget to do it, you forget to do it. and your app crashes if and when you run into an error on iOS. Concurrency is not fun yet. There are some cool, there have been some cool progress with multi-threaded coroutines in native. Luckily, Quizlet doesn't need to use any of that because we intentionally chose to share business logic instead of things like the data layer or networking or persistence. But if that is something that you're interested in, there are some limitations that you need to be aware of. And this is an area where things are rapidly changing. Yeah, and framework interdependencies are a little bit tricky, where until recently, you couldn't have more than one Kotlin multi-platform or Kotlin native framework in an app. Now you can, but there's still this requirement that they're independent of one another. Whereas when we're building this code, you're building in Gradle, you might have your grader might depend on some shared code in a different thing. So right now you have to build one mega framework and consume it from iOS, which is still fine because the iOS client is using all of those things, but it's just a little bit more annoying to deal with. And builds are Mac OS only, which I guess is expected for iOS frameworks. But yeah, despite all those quirks, we were able to get our native, our iOS test suite testing the grader, which was originally testing the JS grader and is now testing the Kotlin native grader. We had a 25 times performance boost, which is pretty ridiculous. And it works relatively well for us. So connecting all those dots together, Kotlin Multiplatform is not without its drawbacks. Hopefully, those slides with all those bullet points kind of illustrated that. But for Quizlet's use case, it was the right fit for us. By porting the grader and using established pain points that we had with JavaScript, we were able to do a very, very detailed breakdown of is Kotlin Multiplatform the right fit for Quizlet. And we found that it was a much more robust solution compared to sharing JavaScript across our clients. Over the past year, we've migrated the rest of our shared code to Kotlin Multiplatform, and we've involved developers from the backend, front-end web, iOS, and Android. We've been working with existing libraries, shared frameworks that we were writing in JavaScript, and we've written brand new stuff in Kotlin Multiplatform, and it's been proving to be very, very useful for us. Some older modules that were very scary for engineers to work in because they were written in JavaScript, they've had some new life breathed into them. We're able to do mass refactors and big overhauls to those things as a result of using Kotlin. And yeah, and thanks to Kotlin Multiplatform, folks from all parts of the Quizlet engineering org are excited to write shared code instead of feeling a little bit hesitant because of the shortcomings of JavaScript. We've consistently found that it's a pretty enjoyable experience for our engineers. Developers who hated the idea of JavaScript like writing in Kotlin, and developers who liked writing JavaScript also like writing in Kotlin. So yeah, is now the time for you all to dive headfirst into Kotlin Multiplatform. It's definitely an exciting time to be doing that. I would not say that it's the ideal situation, the ideal solution for everyone's needs. Kotlin Multiplatform is not perfect, but the ecosystem is growing really quickly. JetBrains has been engaging the community and consistently addressing pain points. If you want to do multi-platform networking, persistence, and serialization, there are real solid libraries out there in Kotlin Multiplatform to do that. We just don't use them at Quizlet, so they weren't really part of our evaluation of the toolkit. But tooling has reached a state where I'd happily recommend using Kotlin Multiplatform for the right use cases. 50 million Quizlet users a month end up touching code that was written in Kotlin Multiplatform in one way or another. And no company should go all in on a tool just because it's really popular right now. So instead of thinking about, how can I use Kotlin Multiplatform at my company, think more about, what are the bottlenecks in our development process right now. Because shared code is not free. It's not one size fits all. As I experienced by a bunch of those companies earlier, choosing the wrong path can end up costing you later. And shared code is only as good as the amount of time that it saves you. So if you end up creating more problems for yourself by sharing code, you might not actually be doing the right thing for your company. So at Quizlet, by keeping our eye on our secret sauce and thinking very critically about what parts of our code base do we want to share, do we need to share, we were able to ship Kotlin Multiplatform, great, but more importantly, we were able to develop a framework for evaluating tools like shared JavaScript versus Kotlin Multiplatform within the context of our business needs. So I hope that our journey and framework for evaluating those tools was helpful for you as you, continue to think about things like sharing code in your projects and organizations. I don't have time for questions or anything. I'm already a little bit over, but feel free to hunt me down after this or tweet at me if you have questions or criticisms. Thank you.